Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to take up a numerical on baseband shaping for data transmission. Please note, this is a numerical on drawing waveforms for the different signaling formats. Let me read out the question first. For the given binary sequence 10100011, sketch the transmitted sequence of pulses for each of the following line code. Part 1 is unipolar non-return to 0. Part 2 is unipolar return to 0. Part 3 is polar non-return to 0. Part 4 polar return to 0. Part 5 bipolar non-return to 0. Part 6 bipolar return to 0. Part 7 Manchester encoding. Part 8 polar quaternary natural as well as gray. And lastly part 9 differential encoding. Right. Let us now start the solution part. We are given the binary sequence BK as 1010011. I am going to start with the part 1 here, which is unipolar NRZ. Let me first show you how symbol 1 and symbol 0 are represented in unipolar NRZ. A symbol 1 in unipolar NRZ is represented by transmitting a pulse of duration 1 TB and let us say amplitude equal to A. Whereas symbol 0 is represented by no transmission for the duration of 1 TB. This is unipolar non-return to 0. Let us now start plotting the waveform. I'll start with the x-axis, which is the time axis. The y-axis is the amplitude axis. Coming back to the binary sequence, you will note that you have 7 bits. Therefore, I will have to now divide the x-axis into 7 equal intervals. This is 0, this is TB, 2 TB, and it continues in this fashion. Now, I will write the bits of the corresponding binary sequence at each bit interval. Let us now start plotting the diagram. For the first bit interval, we have a bit 1, and as per this diagram, a bit 1 is represented by transmitting a pulse of duration 1 TB and amplitude A. So, here I will plot a rectangular pulse of amplitude A and duration 1 TB. The next bit is 0, and for bit 0, you please note we do not transmit any value. So, for bit 0 here, I will simply mark 0 volts between TB to 2 TB. Then we have a 1 again, so I am going to once again transmit a rectangular pulse of amplitude A and duration 1 TB. And for the next 2 zeros, we have no transmission, so 0. Then we have 2 bits, both of them being 1. Therefore, I will now transmit a pulse of amplitude A but duration 2 TB. Right. This is the unipolar NRZ waveform for the given binary sequence. Let us now move on to part 2 of the question, which is unipolar return to 0. Once again, I am going to start by showing how a unipolar RZ scheme is framed for symbol 1 and symbol 0. For symbol 1, we transmit a rectangular pulse of amplitude A and duration TB by 2, and for the remaining half of the bit duration, we transmit nothing. This is symbol 1. For symbol 0, once again, there is no transmission for a duration of 1 TB. That is the same as that of unipolar NRZ. Let us now start plotting the waveform for unipolar RZ. I have here prepared the graph for plotting the waveforms, and I have also written the bits across each bit interval. Let us start with the first bit, which is a bit 1. As we have previously said here, a bit 1 or symbol 1 is represented by transmitting a pulse of amplitude A for a duration of TB by 2, and for the remaining half of the bit duration, we transmit a 0 volt. Coming to bit 0 is transmitted with no transmission, so I will extend the 0 volt from TB to 2 TB. The next bit is a bit 1, so I am once again going to transmit a pulse of amplitude A and duration T, and for the remaining half of the bit duration, I will transmit 0 volt. The next two bits are both 0 0, so I will be transmitting 0 volts for the next two bit intervals. The next bit is 1, so I will transmit a pulse of duration TB by 2 and amplitude A. For the remaining half of the bit duration, 0. Repeat the same process for the last bit 1 as well. Right. This is the waveform for the unipolar RZ signaling scheme for the given data. Now, I will move on to the third signaling scheme that is given, which is polar NRZ. Symbol 1 in polar NRZ format is represented by transmitting a pulse of amplitude A and duration 1 TB. Whereas symbol 0 is represented by a pulse of amplitude minus A but duration 1 TB. This is how symbol 1 and symbol 0 are represented in polar NRZ format. Let us now start plotting the waveform. Right. The first bit here is a bit 1, so I will be transmitting a pulse of amplitude A and duration 1 TB. The second bit is a bit 0, so I will be transmitting a pulse of amplitude minus A but duration 1 TB. This principle is repeated for the rest of the bits. Right. This waveform represents the given binary sequence in the polar non-return to 0 signaling scheme. Whenever a symbol 1 appears, you transmit a rectangular pulse of amplitude A and duration 1 TB. And whenever a symbol 0 appears, you transmit a pulse of amplitude minus A and duration 1 TB. That is polar non-return to 0. Let me now move on to polar return to 0 signaling scheme, which is our fourth part of the question. Right. In polar return to 0, for representing symbol 1, we transmit a rectangular pulse of amplitude A but duration TB by 2, and for the rest of the bit duration, we transmit 0. So, it would look like this. Coming to symbol 0, whenever we need to transmit a symbol 0, we transmit a pulse of amplitude minus A and duration TB by 2, and for the remaining bit duration, we transmit 0 volts. So, it would look like this. Right. With that information, we can now start plotting the waveform. Right. Let us start with the first bit, which is a bit 1. For bit 1, as previously told here, we transmit a rectangular pulse of amplitude A and duration TB by 2. And for the remaining half of the bit duration, we transmit 0 volts. Coming to the next bit, which is a bit 0, as explained here, we transmit a rectangular pulse of amplitude minus A and duration TB by 2. And for the remaining half of the bit duration, we transmit 0 volts. This principle is extended for the rest of the bits. So, bit 1 is represented by a pulse of duration TB by 2, and for the remaining half of the bit duration, it is 0 volts, and bit 0 is represented by a pulse of duration TB by 2, but amplitude minus A, and for the remaining half of the bit duration, we transmit 0 volts. Right. This is the waveform for the given binary data in terms of polar return to 0 signaling scheme. Let me now move on to the fifth scheme, which is Bipolar NRZ. You should note symbol 1 is represented in two different formats in Bipolar NRZ depending upon where it appears. For example, when symbol 1 appears for the first time, it is represented by a positive pulse of amplitude A and duration 1 dB, and when it appears the next time, it is represented by a pulse of amplitude minus A and duration 1 dB. Right, as I said, for the first time when a symbol 1 appears, we transmit a pulse of duration 1 dB and amplitude A, and the next symbol 1 in the data sequence is always represented by a pulse of amplitude minus A and duration 1 dB. So, we should note that in bipolar NRZ, the representation for symbol 1 alternates between plus A and minus A. Coming to symbol 0 is represented with a no transmission for a duration of 1 dB. With that information, let us now start plotting the waveform. The first bit is a symbol 1. So, as per the previous discussion, the first time a 1 appears, we represent it with a pulse of amplitude A and duration 1 dB. The next bit is a bit 0, and bit 0 is represented with no transmission. The third bit is a bit 1 again, and as per our discussion previously, we have to now change the pulse amplitude from the previous one. Previously, it is represented as a positive pulse. So, this time I should represent it as a negative pulse. So, now we will transmit a pulse of duration 1 dB, but amplitude minus A. We have to change the amplitude every single time the bit 1 appears in the data sequence. The next two bits here are 0, 0. So, they are represented with 0 volt. The next bit is a 1. So, we look at the previous bit amplitude, it was minus A. So, I should now represent the current bit 1 with a positive pulse. The next bit is also bit 1, and we see that the previous bit 1 is represented with a positive pulse. So, therefore, this bit should be represented with a negative pulse. Right. That is the representation of the given binary sequence in terms of bipolar non-return to 0 signaling scheme. Let us now move on to the next one, which is bipolar return to 0 signaling scheme. Now, I am going to borrow the concept of bipolar non-return to 0 to explain the bipolar return to 0. So, we now say that for a bipolar return to 0, a symbol 1 and symbol 0 are transmitted with a positive and negative pulse, but this time the pulses will be of TB by 2 duration. So, the first time a bit 1 appears, we represent it with a positive pulse of duration TB by 2 and amplitude plus A. And the next time a bit 1 appears, it is represented by a pulse of duration TB by 2 but amplitude minus A. Symbol 0 is once again represented with no transmission for a duration of 1 dB. This is bipolar return to 0 signaling scheme. Let me now plot the waveform. Okay. The first bit is a bit 1 here. So, for representing bit 1, when it appears for the first time, we transmit a pulse of amplitude plus A and duration TB by 2. And for the rest of the bit duration, we transmit 0. The next bit is a bit 0, so we transmit 0 for a duration of 1 dB. The next bit is a bit 1, so I have to now change the amplitude. Previously it was plus A, so I have to now change it to minus A. So, I will now transmit a pulse of duration TB by 2 and amplitude minus A, and for the rest of the bit duration, I will be transmitting a bit 0. The next two bits are 0 and 0, so I will transmit 0 for 2 bit duration. The next bit is a 1, so I will check the amplitude of the previous bit 1, which is negative. So, this time I will have to transmit a pulse of amplitude plus A and duration TB by 2. The rest of the bit duration is represented with 0 volt. And the last bit is also 1. So, this time I will have to transmit a negative pulse of amplitude minus A and duration TB by 2. This is the representation of the given binary sequence in terms of bipolar return to 0 signaling scheme. Next, I move on to the 7th part of the question, which is to plot the Manchester format. Let me now quickly show how symbol 1 and symbol 0 are represented in Manchester format. Right. In the Manchester format, both symbol 1 and symbol 0 are represented with a doublet pulse. Now, when I say a doublet pulse, it simply means that half of the bit duration is positive and the remaining half is negative. So, a symbol 1 is represented by a doublet pulse of amplitude plus A, and for the remaining half of the pulse duration, we transmit a negative pulse of amplitude minus A. However, when we are asked the amplitude of symbol 1, we say it is plus A only. Coming to symbol 0, it is exactly the reverse of symbol 1. That is, we start by transmitting a negative pulse for the first half of the bit duration, and this is amplitude minus A, and for the remaining half of the bit duration, we transmit a positive pulse. The amplitude of this pulse is said to be minus A. Let me now plot the waveforms for the Manchester format. Right, the first bit here is a bit 1. Bit 1 is represented with a doublet pulse of amplitude plus A for the first half of the bit duration, and for the remaining half of the bit duration, we transmit a negative pulse. I will not be drawing the vertical line here because if you look at this, we have a 0 in the next bit duration. And bit 0 is represented by transmitting a negative pulse. So, by drawing a line at 1 TB, it means the data goes back to 0, which is not a practical case. So, coming to the next bit, which is a bit 0, we start by transmitting a negative pulse for the first half of the bit duration, and for the remaining half of the bit duration, we transmit a positive pulse. The next bit is a bit 1. So, we start by transmitting a pulse of amplitude plus A for the first half of the duration, and for the remaining half of the bit duration, we transmit a negative pulse. This is the representation of Manchester encoding for the given binary data. Let me move on to the next one here, which is polar quaternary, both natural as well as gray. To start with this, I'll have to show you how the natural and gray codes are represented for each level across the input. Please note it is a quaternary, therefore there are 4 input symbols. Let me now plot a very small table to give you an idea about the levels and the code word for each level. The 4 levels are minus 3, minus 1, plus 1, plus 3. In the natural code, minus 3 is represented with 0, 0, minus 1 with 0, 1, plus 1 with 1, 0, and plus 3 with 1, 1. In a gray code, it is 0, 0, 0, 1, 1, 1, and 1, 0. Please note, the change is only in the last 2 level code words. Please note that each level in both the natural and gray code represents 2 bits. So, the length of the sequence given should be even. In the given numerical, BK is equal to 1010011. It is of odd length. So, let me now just add another bit, let us say bit 0, to make it even. So, whenever I start encoding the data, I will take 2 bits at a time. I will go to the table here. I will identify what is the corresponding amplitude level, and then I will mark the same on the waveform. Right. Let us start with the polar quaternary natural encoding first. Let me mark the amplitude levels here. We have 1, 3, -1 and -3. Let us start the plotting now. The first two bits are 1, 0. Go back to the table, search for 1, 0. 1, 0 represents level +1. So come back to the diagram and plot a rectangular pulse of amplitude +1 but duration 2 TB, because we have taken 2 bits at a time. Next, go to the next 2 bits, which are 1, 0 again. So the same continues. Please note, now I have to eliminate this line. The next 2 bits are 0, 1. Go back to the table. 0, 1 is represented with -1. So come back and plot a rectangular pulse of amplitude -1 and duration 2 TB. Here I have not added the last bit, which we have assumed to be 0. So, and let this be 8 TB. The last 2 bits are 1, 0. So, go back to the table. 1, 0 represents +1. So, I now change the amplitude from -1 to +1. So, I now change the amplitude from -1 to +1 and I draw a rectangular pulse of amplitude +1 and duration 2 TB. This is the waveform for the natural code representation for the given binary sequence. In a similar fashion, let me quickly show you how gray coded waveform would look like. Right, let us start the waveform now. The first 2 bits are 1, 0. Go back to the table. 1, 0 here is represented with +3 volts. Come back to the waveform and plot a rectangular pulse of duration 2 TB but amplitude 3. The next 2 bits are also 1, 0. So, I extend the same waveform for the next 2 bit durations as well. And now I will remove this line from the 2 TB point. The next 2 bits are 0, 1. Go back to the table. 0, 1 is represented with a amplitude level of -1. So, I now change the amplitude level from +3 to -1. This is for 2 bit duration. The last 2 bits are once again 1, 0 and 1, 0 is represented with a level +3. So, now I will write a positive rectangular pulse of duration 2 TB and amplitude +3. This is the gray coded representation for the given binary sequence. Please note, both the gray and natural are plotted in polar quaternary form. Coming to the last part of the question, we have differential encoding. Now, an important thing to know about the differential encoding is it requires an initial bit. And for this case, let the initial bit be represented with a 0. Now, the differential encoding says whenever a bit 1 appears across the input, the amplitude level should not change and be retained as it is. So, I will say no change in amplitude here. And whenever a bit 0 appears across the input, the amplitude has to now invert. So, I will now say invert the amplitude. Please note, this is only a convention and I can change this convention for bit 0 and 1 respectively. Right, let me now start with the diagram. As I said, the initial bit is taken as 0. Right, let us start the operation. Here we have said the initial bit is 0 and let 0 be represented with a negative pulse of amplitude -a. We have used polar representation for bit 1 and bit 0 here. Coming to the first bit in the given binary sequence, it is a 1. So, come back to the convention here and look at this. Bit 1, no change in the amplitude. So, you continue to transmit the same amplitude for the next bit duration as well. The next bit here is a 0 and according to the convention, whenever a 0 appears, I have to now invert the amplitude. So, previously I was transmitting -a, so I have to now change it to +a. This I have to transmit for the next 1 bit duration. The next bit is 1, so I have to now continue transmitting the previous amplitude for the next 1 bit duration. The next bit is a 0, reverse the amplitude of the pulse. The next bit is again 0, so once again reverse the amplitude of the pulse. The next two bits are 1, 1, so continue transmitting the previous amplitude for the next 2 bit durations. This is the waveform for the differential encoding scheme for the given binary data. Right, that is the solution for this numerical, and with that we come to the end of this video. If you like this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.